Okay, welcome. We are about to do Newton's first law, which is also called the law of inertia. Now, Newton said that all objects will continue to move in uniform motion in a straight line or remain at rest unless acted upon by an external outside with external unbalanced force. So let's have a look at the elements of this here. Uniform motion in a straight line. That is quite important because uniform motion and straight line, if we have uniform motion, we have no change of speed. So no change of speed. And the straight line means no change of direction. Now those two important points, speed and direction, is magnitude and direction of the velocity vector. So in other words, it's saying no change in velocity. So no velocity change. And we know that as simply saying we will not accelerate. So all objects will remain in their same, they will not accelerate, they will not change their velocity. Now this velocity could be motional velocity, if I use that word. So we could be at motion already, or we could be at rest. Because velocity at rest is still velocity, and it's a velocity which equals 0. So Newton is saying that we'll either be stopped or we'll continue to do exactly what we have been set out to do. We are not going to change. And the only way we can change our motion is if we have an outside force. This is an outside unbalanced force. Remembering that we can always have many forces acting upon us, but if one or more of them unbalanced, we move or accelerate in the direction of that force. Right. To really to dramatise this idea of Newton's first law of inertia, we can actually have a look at it in practice. And sorry, just get that one right. And the best way is actually to see how it works in terms of the motion of things in a car crash. So I'm just going to show you a crash test dummy of a car crash. So just pause the video for 5 seconds. Okay, this is a video I've just taken off YouTube, and it's showing 2 children in the back seat, one restrained and one unrestrained, and we are going to collide this car very soon. So let's have a look at the video as it moves. So the car moves forward, it stops, and we notice that the child, which is unrestrained, continues to move as it was before unless it is constrained by an outside force, which is right now. So having a look at that again, turning it to its position, pausing it. So it's at this, just before this moment here, let's go here. The car is moving forward. Now the car will actually collide, so it will stop because the car is now being acted upon by an external force, so it changes its motion. But the child here in the actual passengers, the back passenger seat, is unrestrained, so it's going to continue in the motion, the same velocity as the car. So I would like you to look at how fast the child is moving and how fast the car is moving. So the car is moving now, and notice that the child moves at the same rate as the car forward. And it will keep on doing that unless it's acted upon, and unfortunately now is acted upon by the dashboard, which is the external outside force. So inertia in this case is very deadly, but inertia, you can see how inertia makes the motion continue. The child there was already travelling, and it continues to travel at the same speed. It doesn't get faster, it doesn't get slower until it gets acted upon by an external force. Okay, we're going to have a look at some of these true, false and depends questions. The first one I'm going to pose is if an object changes speed, then an external unbalanced force must be acting. And we always have to work out whether or not this is always true, always false, or depends. So I'm going to give you a few moments after each of these to have a few moments to pause the video. So here we go. If an object changes speed, then an external unbalanced force must be acting. Now, is it always true? Is it always false? Or does this situation depend? So sometimes an external force is acting or sometimes it's not. Just pause the video and come up with a conclusion yourself. Right, let's have a look at what you said. So I wonder if you said it's always true. So a change of speed. A change of speed means we have got faster or slower. So we have acceleration. And acceleration must be caused by a force. That force that causes that acceleration must be unbalanced. Otherwise, if it was balanced, it would not cause any acceleration. So this is always true because we have acceleration. So I hope you got that one right. Let's move to the second one now. The second one says, if an object is moving at a constant speed, then no external unbalanced force is acting. Take a few moments and come up with that one. Right, we've unpaused the video. Constant speed. Constant speed. So it's not saying that it's moving at constant velocity. So what is constant speed? Constant speed means there is no change. Let's do that, undo that. There is no change in the magnitude of velocity. This is not saying we haven't got a change in direction. There could be a change in direction. If there's a change in direction, then we know that change in direction is also called acceleration. So, this time, if an object is moving at a constant speed, oops, that's the wrong colour, constant speed, then no external force is acting. Well, that's not exactly true, okay? It could be that it's travelling at a constant speed, but it's travelling in a circle or in a curve. And that means that there is change, it is velocity, it is acceleration. Acceleration must be caused by a force. So we could have ticked always false or depends. I would go more to depends because it could be, it depends if we are changing direction. Okay? But this statement is by itself just false, but it depends on the situation. So I'm going to go for depends in this situation. Okay, let's have a look at our next one. If an object changes direction, then an external unbalanced force is acting. Is this true, always false, or depends? So take a few moments to pause the video and come up with an idea. Okay, if you've unpaused the video now, let's have a look at things. If an object changes direction, then we must have an unbalanced force. Well, this is very similar to the one we just had a few moments ago. A change of direction automatically means a change in velocity. That's a change there in velocity. Change in velocity is acceleration. Acceleration must be caused by an unbalanced force, so this would always be true. Okay. Let's move to the next one. That was a simple one. And move it down. Okay, this is a... If an object is at rest, then the object has no external unbalanced forces acting on it. If the object is stationary. Now, take a few moments, pause the video, and see if you agree, disagree, or have a depends on this. Okay, let's see what you decided. Okay, if the object is at rest and it is not moving, then we have zero velocity. Okay? Now, zero velocity can't change direction, can't change speed. So there is neither change in its magnitude or the direction, so therefore there is no acceleration. If there is no acceleration, we have no force. So in this case here, there could not be any force, external unbalanced forces. There could be two forces on it, but they could be balanced. If that's like a 5 Newton forward and a 5 Newton back on an object, then that's a balanced force. That's not an unbalanced force. So it's always true in this situation. I'm quite happy if you want to argue the tosses on all these. Okay. Right, the next one. If an object is changing its displacement, then an external unbalanced force is acting. So in other words, if it's changing its displacement. So let's have a look at the changing its displacement, then we have a force. Okay. Take a few moments, pause the video, think about it, and then come back. Okay, back now, let's have the changing displacement. It's not saying we're changing direction, so there is no indication here that there is a change in direction. It's just moving. Now, it doesn't say if it's moving at a constant speed or constant velocity, and it's not saying if it's accelerating. Okay? So if it's changing, if it's a constant velocity, which means that there is no speed change and there is no direction change, then there'll be no acceleration. However, it just says it's changing its position. If it's changing its position, then simply it could be either accelerating or not accelerating. If it's acceleration, then there would be a force. If it's not, then it wouldn't have a force. So this is a definite depends. It depends on how it's changing its displacement. If it's changing displacement by accelerating, then it would have an external force. Okay, let's move to the next one. And this one. If acceleration is positive, then the object must be getting faster. And conversely, if acceleration is negative, it must be getting slower. Okay, so let's take that apart. If we have positive, we must be getting faster. Negative acceleration, we must be getting slower. Okay, pause the video and take a few moments to come to a decision. Okay, welcome back. Okay, so let's put a frame of reference. As we know, a frame of reference indicates a positive direction and a negative direction for our motion. So let's move this way. Okay? If we are accelerating in that direction and we go that direction, we get accelerating that way, we get a force that way, we must be getting faster. Okay? So that's fine. Okay? But the word faster is very ambiguous here. Okay? Is that getting more positive, getting more negative, or so on? Okay? If we are accelerating, if we are moving this way and we have a negative acceleration this way, then we'll get slower. So that's good. Okay, so it looks like it's true. Okay, but what happens, however, if it doesn't say if we are travelling in the positive direction to begin with? What happens if we were travelling in the negative direction to begin with? Then, if we had a positive acceleration this way, we would be getting technically slower because I would start to slow down in the negative direction. If, however, I was accelerating this way, I would start to accelerate in the negative direction and I'd get faster. So this one is a definite depends. It depends on which direction you're travelling first, and also what do you mean by faster and slower? They are ambiguous terms when we're talking about speed and velocity. They're not technical enough for us physicists. Okay. Now that we've had a look at the motion of objects as forces, balanced or unbalanced, act upon them and how they interact, we can now start our worksheet here. So let's go through doing our motion 6 worksheet. This is changes in motion and inertia. The last part of our work has been looking at the forces on cars, especially on objects. So here we are. The first question here is: a car is travelling down a straight stretch of track. The forces X and Y are in the horizontal direction as shown in the diagram, and they are the same magnitude but opposite in direction. Just to understand what these directions are, X must be, because it is in the direction of a car's forward direction, this is what we call the driving force. So this would be our driving force. And Y, being in the reverse direction, would be one of our resistance forces. Not when I say one of, that's not exactly true. So these are our resistance forces, not one of. Resistance. Oh, I spelled resistance wrong. Okay, we'll get that. No problem, Chick. Okay, now we know that resistance forces are not a single force. There is a whole lot of forces here. This is road friction. There is air resistance. There is just engine friction, because that's the reason why we have to put oil into our car. We just have all the frictions inside. And we also have different types of other frictions, static and kinetic, all these types of frictions which are resisting our motion forward, sometimes just called together rolling friction. Okay, so those are the two. Now, because our forward and back are equal to each other, there is no balance, there's no net force on the car, so there is zero. So the car has, according to Newton's first law, will continue in its state that it was in originally, unless acted upon by an external unbalanced force. There are no external unbalanced forces. Both of these equal each other. So Newton's first law here will say that this car is going to do what it did before these forces were applied. Okay. So we're told that it's travelling down a straight stretch of road. Okay. So will it continue to travel? Yes, it will continue to travel. Will it continue to stay in a straight line? Yes, it will continue to go in a straight line. Even though it has two individual forces on it, it will just continue to move. Similar to like a skater, just skating along underneath on the ice. Okay? So the next question along underneath that says, justify why there exists no net external forces. That's simple enough, because that they cancel each other out. And the car is travelling at a constant velocity. Explain how it's given. This is given that there are no external forces. So I've just explained that because according to the law of inertia, it states that it will continue to go on the path that it was always on, which is a straight path at a constant velocity. C says, state two possible causes for resistance force Y. I've gone through those, so you could be stating anything from air resistance, rolling friction, static friction, engine resistance, friction with the road, and so on. D, the driver uses the brakes to bring the racing car to a stop. On the diagram, we're going to draw these forces. Now, when we're drawing these forces, one thing that people who don't as yet have a license don't understand is that we don't press the accelerator on a car, the accelerator pedal, and the brake at the same time. So the foot would be removed from the accelerator. So remember, we normally have a driving force. Okay? When we are braking, the driving force is removed. And we only have one force, well, one major force going back, which we call, it's still resistance force. And this resistance force is now made up of the braking force plus all the other, which is air resistance and friction as well. Okay, but now we have a large component called the braking force, which is the friction between the pads of the actual wheel and the actual brakes themselves. Okay. So as the car slows to a stop, however, what's going to happen? So let's just say this person here, the driver, puts on a brake. This is the force for braking. Okay? Remembering we also had a whole lot of other resistance forces. So the braking force, this braking force up here, it remains the same because the pressure on the brakes are always the same for the driver. But what's going to happen here is some of these forces are going to be reduced. So the air resistance goes down because we start to get slower, and air resistance gets less as we get slower. So you'll have a loss of air resistance, as well as also some of the other frictional forces become less. So the friction starts to go down as well because we're getting slower. So what happens is we originally start with a backward force, which is FB, braking force, and FR, and then it becomes, as we brake and slow, just simply down to FB. Okay, as long as we do not release the thing. So this force here becomes less and down reduces to 0. That's as long, of course, as we don't depress the braking pedal any heavier or release it any lighter. Okay. Let's look at the next part. The next part says that as this happens, the passenger in the car feels pushed forward into his seat. Why does this happen? So let's remember here is the car. Here's the car. Let's just put our car again from the last lesson. Not last lesson, last question. And here is the man in the seat. And we are travelling originally in that direction, and he feels as if he's pushed forward. And why does that happen? Because he continues to move with the original motion of the car, because that's the direction it was travelling. And when we put on the brakes, he continues to move forward. Luckily, I'm hoping he does, he will have a seat belt, and that seat belt will keep him fastened into that, I think, but he's pressed against the seat belt now, so he moves forward, and hopefully the seat belt then pushes back with equal and opposite reaction forces. Okay, right, so our hopefully is quite safe. Now, the next part is the driver now depresses the accelerator pedal to speed up. What will happen to the situation? So here is, once again, we're going to draw a force diagram. Now, force diagrams are simply using boxes rather than three-dimensional shapes. So the driver now depresses the accelerator. So the driving force becomes quite large. As a result, the resistance forces increase. They can never be any bigger than the driving forces. If the resistance forces were bigger, then it would move backward. So just make sure that you would have a smaller arrow at this end. Okay? And we need to look at vertical forces for the first time here. It says, and vertical forces. Now, the two vertical forces that are on the car are the weight force, which pulls it directly down towards the centre of the Earth, which is mg, and there is an equal and opposite normal force. Now, the normal force is created because of what the this line is not meant to be here. I'll just put it in though just to show you. That's the road surface. Now, the weight force pulls the car onto the road, and as a result, the road has to push back up against the car. This pushing back up is called the normal force. It's an equal and opposite reaction force according to Newton's third law. Okay? They have to be equal. If weight force, the mg, was any bigger than normal force, the car would sink into the road. And if normal force was bigger than weight, it would rise into the air like a balloon. So they're the four forces. Okay? Just make sure that we are putting them in, that these two forces, that is equal to that. The driving force definitely has to be much bigger than the resistance force. And in fact, the driving force can never be less than the resistance force, otherwise magically it would just return or reverse. Okay. Once again, we have to explain what will happen to the force, this over here, the resistance forces, as the velocity increases. Remember, as the velocity increases, so will air resistance. Okay, so air resistance increases, so what will happen is this will get longer and longer. Okay, but once again, it cannot exceed the driving force. Okay, and the last part here, just a few seconds, says the passenger in the car feels pressed into their seat when this happens. Why is that happening? Okay, so let's just put our person, and we'll just put it up here. Okay, there's the person, and we're just going to make a very, very simple seat. Okay, here it is. Okay, there's our seat. The seat is accelerating forward. Okay, the person in the seat itself doesn't want to accelerate. They've got inertia. They resist that force. So therefore, they are trying to stay where they are, and they resist this motion. So therefore, they get pressed back into the seat because they are trying to stay at the same velocity that they were before, which was stationary or whatever. So we feel pressed into our seat as we accelerate forward. So that's how we explain that in terms of the first law. We don't want to change our motion, so we resist it. This person here is trying to stay in a constant state, but unfortunately the seat is acting upon him, pushing him forward. Okay, rightio. Here's a challenge for you to do. There are 3 situations down here, which is a wallet on a dashboard appears to move to the left as a car turns around, turns to the right. I've had that happen to myself, and in fact it's fallen out the window. So why does that happen? The second one is riders on the graviton at the Easter show are pinned against the wall. We might know this as the rotor at Luna Park. Why does that happen? And the unsecured load of a truck is left behind as the truck accelerates forward. And we also might see this as a magician's trick where we pull the tablecloth out from underneath crockery which is on the table. That's the same situation. We've got to explain each of these situations in terms of Newton's first law. Okay? Why does the wallet tend to move? Why do you get pinned to the back in your gravitron? And why can a truck leave its load behind? Okay? The solutions to this will be on the website. Okay, thanks very much.